Hi, good afternoon, everyone, and thanks for hanging this far into the day. Thanks, Pratik, for the introduction. So I'll be talking about protecting the privacy of BLE device users. I did this work with Kyu-Han Kim from Hewlett Packard Labs, while advised by Professor Shin from the University of Michigan. So Bluetooth Low Energy, also known as BLE, Bluetooth 4.0 Plus, Bluetooth Smart, as opposed to the regular Bluetooth we're used to, like Bluetooth Classic, is Bluetooth 6's answer to the Internet of Things. It's supposed to provide short-range communication between less powerful and energy-constrained devices, like your Fitbits, for example, and more powerful clients like your smartphone. Now, Bluetooth SIG lists around 74,000 unique products, unique BLE-equipped products on their website. In the year 2013, more than 1.2 billion BLE-equipped products were shipped, with this number expected to hit 2.7 billion devices in 3 or 4 years. So the most important part of the BLE is the LE, the low energy part. And the reason is that the protocol places very low energy burden on these less powerful devices or energy constrained devices. In fact, most of the time, these less or energy constrained devices spend their time in standby mode, where their functionalities, network functionalities, are turned off. Occasionally, they wake up and advertise their presence by broadcasting beacons to let others know of their presence. Now, on the other hand, you have your more powerful clients, like your smartphones, scanning all the times for these advertisements. When they receive an advertisement of interest from a device of interest, they initiate a connection, in which case they'll be in the initiating state. Now, if the smaller device responds to the connection request, both devices will move into the connection stage. At this time, your less powerful device, or your Fitbit, for example, will be the server because it has information to offer. And on the other hand, your client device will be, or your smartphone will be the client because it is fetching the information. Now, this whole connection process and this whole protocol is enabled by advertisements. A device is supposed to advertise its presence to enable scans and connections. The BLE protocol defines 3 dedicated advertisement channels, 37, 38, and 39, and it also defines 4 types of advertisement messages, the most important of which are the direct advertisements and the indirect advertisements. Direct advertisements are those used by BLE peripherals, like your BLE keyboard, for example. So you turn on your BLE keyboard, it starts advertising at a very high frequency for 1.2 seconds. Your smartphone will be scanning for these advertisements that will only contain 2 fields, the source address and the destination address. Your smartphone, which will match the destination address, will pick up the advertisement, will connect to it. And then we have the more general and perhaps the most common type of advertisements, which is going to be featured throughout this talk, which is the indirect advertisements. These are periodic, or let's say quasi-periodic advertisements, in which a device advertises its presence, waits for a short amount of time to accept connections, and then sleeps for an advertisement interval, which is predetermined and can vary between 20 milliseconds and 10.24 seconds. And then, and that's very important, it sleeps for an additional random delay between 0 and 10 milliseconds. And that's BLE's version of channel access control. And it's supposed to minimize the probability of collisions of different advertisements from different devices. Now, the advertisement message contains the source address of the device along with many identifying fields, for example, like the device's name. Now, having a device regularly advertising its presence is not very desirable from a security and privacy standpoint. So the BLE protocol designers have anticipated that, and the protocol contains some security and privacy provisions. Mainly, they have borrowed the pairing and bonding procedures from the regular Bluetooth, so that only authorized clients are supposed to connect and access sensitive services on your BLE device. They have address randomization, which has been proposed in Bluetooth 4.2 protocol, in which the device is supposed to change its address frequently in a manner that seems random to other sniffers and eavesdroppers, but predictable and deterministic for an authorized client. And finally, we have the direct advertisements that I just described, which are supposed to prevent user tracking because they are not periodic and contain too less information. Now, to evaluate how these privacy and security provisions are really effective in practice, we developed an Android app, which basically scans for BLE advertisements in the vicinity. We deployed this app in 3 different scenarios. While interning at HP Labs, I gathered BLE advertisements in the area for 40 days. I also recruited 13 participants from our school in Ann Arbor, and we were able to collect data for around 2 months. I'd also relied on the Phone Labs testbed from sunny Buffalo, where I was able to recruit 86 participants and also collected data for around 2 months. So what we found is perhaps not so surprising for the most of you. Most of the devices do not rely on the more private direct advertisements. In fact, just from these indirect advertisements, we were able to detect or observe more than 214 unique types of devices, not just unique devices, unique types of devices. We also found that this scheme of Anders randomization really is not effective in practice. Many advertisements contained revealing names of the devices, as you can see in that left-hand table over there. For example, we're able to sniff a glucose monitor. Also, devices used consistent addresses over time, as you can see in that middle table. For example, while in HP, I was able to scan for around 40 days, and for out of these 40 days, 37 days, several Fitbit devices maintain the same addresses. Some devices do actually attempt address randomization, as you can see at that right-hand table over there, by flipping 3 or 4 bits at each advertisement session, which is not very effective in terms of randomization. We also found that device pairing and bonding probably is not implemented well in practice. We're able to connect to different devices without an existing trust relationship. For example, we're able to see the battery values of different Fitbit devices as they change in runtime. And we're able to connect to other devices like this digital pen over here that has a value that was changing frequently, which I'm not sure what that is, but could be revealing. So basically, if you have an eavesdropper who's scanning your advertisements, can track you over time from these consistent addresses or from poor randomization. They can profile you by studying, for example, your health condition, as we saw from this glucose monitor. And in extreme cases, you can envision an attacker actually posing threat to user or posing harm to user by, for example, fingerprinting a sensitive security system from a distance and then exploiting the vulnerabilities that might exist in it. So our objective in this talk is to effectively fend these threats to BLE device users. But very importantly, we need to do that in a device-agnostic manner, meaning that we're not here proposing any additional BLE privacy. We're not proposing any additional privacy enhancements to the BLE protocol, because this will be very hard, if not impossible, to deploy. This will require actually pushing a firmware updates to these thousands of devices that are existing out there. And as we know from our operating systems experience, like from the case of Android, for example, one operating system maintained by one company, a majority of these Android devices, because of some ecosystem fragmentations, are out of date. Now think about these millions of devices out there with thousands of manufacturers and developers that are really not interested in developing firmware updates. And then we have to rely on external hardware to enact this security and privacy protection. So for usability and deployability, we'd like for this hardware to be commercial off the shelf. And for obvious reasons, we'd like to have this system working with as little user intervention as possible. And our answer, as you might have guessed, is BLE-Guardian. So BLE-Guardian is a system from a high-level standpoint, has 2 main components. It has a hardware component, which is basically an external Bluetooth radio that you can attach to your gateway or to your host, such as your smartphone. And it will enact privacy and security for the set of BLE devices around you. Our choice of implementation was Ubertooth 1, an available open source Bluetooth development framework that allows us to transmit and receive on any BLE channel. We also developed user-level apps that run on gateways and, for example, like an Android app that allows the user to configure BLE-Guardian and to update the firmware of the Ubertooth radio when needed. So when you first run BLE-Guardian, it will scan for nearby devices, as you can see at that UI over there. The user can designate one or more devices to be hidden. That's the task of the device hiding module, which will prevent unauthorized entities from scanning or observing said device. And then we have the access control module, which will only allow authorized clients to view and connect to said devices, to these target devices, and in the meantime we'll be scanning or we'll be keeping an eye on unauthorized connection requests to our devices, and will alert the user such in case. So at a high level, we have two main components. We have the device hiding module, which will hide the device from everyone, and we have the access control module, which should only allow authorized clients to see the device and connect to it. I will start describing the device hiding module. So, to hide a device, we need to prevent others from correctly decoding its advertisements, because advertisements are the only mean by which a device presence is known to others. So intuitively, to prevent others from decoding these advertisements, we're going to jam them. But that's challenging for two reasons. Because we need to jam precisely at the same moment the device is advertising, because if we miss the advertisement, we're leaked information about the device. But we can't just keep jamming all the time, because that's harmful and that's not something that we want to do. Now recall that each device will advertise at a pseudo-periodic pattern, right? So there's the advertisement sequence, and it will sleep for a random delay between 0 and 10 milliseconds. So we need to anticipate that. And the protocol defines the 3 advertisement channels, but it really doesn't identify the sequence it follows advertising on these channels. So it's not necessarily that it has to advertise at 37, 38, 39. So in the paper, and I'm not going to delve deeply into that, we have the protocol that we use using a single radio. You can learn the advertising sequence on these channels. So BLE-Guardian will go into a learning phase to identify the advertisement interval of the device. It will observe different advertisements of the device and will monitor the inter-advertisement time. Now, the best estimator of your advertisement interval is the average of these advertisement intervals that we observed minus 5 milliseconds, which is the average of this random delay, assuming that its distribution is symmetric. So if the device last advertised at a time instant Tn, nominally would expect the next advertisement to happen between Tn plus advertisement interval and Tn plus advertisement interval plus 10 milliseconds. But now we don't really have access to this advertisement interval. We have access to an estimate of this advertisement interval, which we denote advertisement prime, and it's advertisement plus minus error. So we expect the next advertisement to happen between Tn plus advertisement prime minus error and Tn plus advertisement prime plus error plus 10 milliseconds. And we denote this time interval as the monitoring interval. So during this monitoring interval, BLE-Guardian will be aggressively sampling the channel RSSI to see if there's a transmission taking place. When it detects a transmission is taking place, it immediately moves and starts jamming the channel, and then follows the advertisement sequence of the device to effectively hide it. Now, there are more involved cases of having more than one transmission happening at the same monitoring interval. I'm not going to go into that. You can also see the details in the paper, but that's something that BLE-Guardian handles as well. So at this point, BLE-Guardian has hidden the device, so nobody can actually access it. And if nobody can actually see the advertisements, nobody can issue connection requests. So how do we enable connection requests from authorized clients? And that's the task of the access control module. So we have it has two main subtasks, if you want to say. It has an authorization submodule that allows us to authorize clients to access this BLE device. And we rely on Bluetooth Classic as an out-of-band channel to enable this authorization process. Because most of these clients and the host BLE-Guardian is attached to are smartphones or gateways. And their Bluetooth chips are dual mode, meaning they have BLE and Bluetooth Classic. And so BLE-Guardian runs as a service on this Bluetooth Classic with a known UUID and Bluetooth address. And these are made public. So when a client that wishes to authorize herself will attempt connection to BLE-Guardian service, which will prompt a pairing request. And the user has a choice either to approve or deny this request. And if the user approves such a request, then the client will be authorized by the user to access her BLE devices. Now, how actually does this access take place is the job of the connection enabling submodule. So Every connection request will contain a set of connection parameters that indicate how the connection should take place. And the protocol defines 3 million different combinations of these connection parameters. Now, BLE-Guardian will choose a particular set of these parameters and will communicate them over the out-of-band channel to the client for reasons that will be evident in a little bit. Then, immediately after the device finishes advertising on the last channel, BLE-Guardian will stop jamming. And it will advertise on behalf of the device using the same address, but it will reduce the amount of information leakage. So what happened now is the following. The client is scanning for an advertisement, and it received one that looks just like from the target BLE device. At the same time, the target BLE device is listening for connection requests. And this way, the BLE connection process is not broken. It's still the same. We haven't changed anything of how this BLE protocol works. And the client can just issue a connection request using these particular connection parameters that we provided earlier. And this is how we distinguish this authorized connection request from unauthorized access requests, because the probability of the attacker guessing these connection parameters is very low, and it will not be able to mimic a connection request. So if we observe a connection request that does not contain such parameters, we immediately move and jam it. And at this point, we'll have a legitimate connection taking place. Now, the protocol doesn't specify that the device has to stop advertising after it connects. It can still advertise, but with non-connectable advertisements. BLE-Guardian still jams these advertisements, and data exchange can take place according to the channel hopping sequence that has been pre-negotiated. So to evaluate BLE-Guardian, we focus on 3 main aspects: the distance over which it acts the privacy protection, the impact on the advertisement channel, and the energy overhead when connected to a smartphone. So we're going to start with the cutoff distance. Now, BLE-Guardian is limited in terms of transmission power that we can use. BLE-Guardian basically will, because of FCC regulations, basically, it can transmit using the same power as a Bluetooth Class 1 device. So the farther BLE-Guardian is from the actual target device, there will be an area around it over which the attacker can still receive these advertisements and possibly issue connection requests. So to evaluate how, and we call this the cutoff distance. So to evaluate how this cutoff distance changes as a function of the distance between BLE-Guardian and the target BLE device, we performed 2 experiments by which we fixed the position of a BLE-Guardian of a BLE target device advertising at the highest possible frequency, and we moved BLE-Guardian 10 centimeters apart. We also had the 2 scenarios where BLE-Guardian was covered by a backpack and exposed, and we relied on a TI sniffer that allows us to sniff BLE advertisements that fail the CRC check to see if it's receiving advertisements or not. And we also relied on the Galaxy S5 to monitor its cutoff distance. As you can see, the cutoff distance is smaller as the distance between BLE-Guardian and the target BLE device is smaller. And the takeaway message here is that even when BLE-Guardian is 3 meters far from the target BLE device, the adversary has to be within 1 meter to be able to issue any connection request. So it has to be very close to the user. We then evaluated the impact on the advertisement channel. For this scenario, we had a Broadcom BLE chip advertising at 3 different advertisement intervals. We also had 2 innocuous BLE devices advertising at the highest possible frequency, which corresponds to 20 milliseconds advertisement interval. And we had 15 background BLE devices advertising at different advertisement intervals. And these show these box plots show the distribution of unnecessary jams each monitoring interval that I described before. So the higher, the worse, meaning that we're issuing jams where we should not be doing that. When the device is advertising at the highest possible frequency, the probability of having other devices advertising within its monitoring interval is higher. So possibly you might have to jam more. But as you can see, all of the medians are around 0. So in 50% of the cases, we don't issue any accidental jam, with the maximum number of accidental jam being 2 or 3. As we use higher advertisement rates, the probability of collisions will be smaller. Less devices will be advertising during these monitoring intervals, and we're going to be issuing less and less accidental jams. Now, in the paper, we also have the impact of BLE-Guardian on particular innocuous BLE devices. We're not going to show it here. And finally, we evaluated the energy overhead of BLE-Guardian when it's attached to a smartphone, with Galaxy S5 in this case, Samsung Galaxy S5 in this case. It's worth noting first that BLE-Guardian has no energy overhead whatsoever on target BLE devices or authorized clients, because basically we're not touching them, we're not doing anything with them. But when it's attached to your smartphone, so there's some power cost you have to pay to power it. But we also measured the additional overhead when it's protecting up to 10 devices, and we found that overhead to be at most 16% when we're, as I said, protecting 10 BLE devices at the same time, advertising at different advertising frequency. And the reason for this low overhead that BLE-Guardian is not in receive and transmission mode all the time. It only receives for this monitoring interval and jams when it actually senses an advertisement on the channel. So in conclusion, I described BLE-Guardian, which is a system that we designed to enact privacy protection for BLE device users. It is device agnostic and relies only on commercial off-the-shelf hardware, as you saw. It has low energy overhead and low overhead on the advertisement channels. As part of our future work, we're exploring to extend to other short-range communication protocols like Zigbee, which features some similar beacon-based communication. And we're considering, or actually investigating, whether we can implement BLE-Guardian over Bluetooth chips that might have open source firmware as to not use an external hardware anymore. And thank you.
Hi, thanks for your talk. Can you just go back 2 slides?
2 slides?
Yeah, one more. There. That number looks really high to me, the idle power.
Yes.
That's over a watt. That's over a watt, idle power.
Yeah, it's very similar to when you're powering a Wi-Fi chip on your device. So it is a bit high. So the idle power is a bit high. Yes.
Yeah.
So it corresponds to, so when you're running your smartphone and you have like Wi-Fi turned on, the power will be somehow like
right,
this.
But that is the idle power when the radio is on or when the radio is off?
No, this idle power when the radio is on.
On, okay.
That
makes more sense. Okay, thanks.
All right, let me remind the audience that this session is your last chance to ask questions, so don't be shy. And as you're thinking about one, Kassem, could you talk about potential limitations and challenges of deploying your technology in real commercial devices?
In real commercial devices? I mean, or you mean real environments? Because
right, real environments.
So a major limitation that we need currently for the current implementation, current prototype, that we need external hardware. Which means, for example, if you're wearing your Fitbits and you're running, so you need this Bluetooth to be connected to your phone as you're running. So there's the energy problem first. The other problem is that this power limitation. So as you saw, like 3 meters, we already lost a meter. Now think about your home environment and you want to attach this to your, say, Raspberry Pis or your access point if it is BLE-equipped. So you might have to study how you can deploy multiple of these as to enact effective privacy protection. So it's not really straightforward at this time to deploy in real environments, but I mean, we're going to move towards this direction.
Let's thank Kassem again.